These are the notes for static electricity. This unit is going to involve electrical forces, methods of charging, types of charge, and conservation of charge. First, I'm going to begin by talking about electrical forces. Electrical forces are created by the attraction and repulsion of charged particles called ions. Anytime an atom is either positively or negatively charged, we call that an ion. We call it an atom when the positive and negative charges balance each other out. These charges are also part of the electromagnetic force. Uh, and this is the new force that we are going to be working with in this particular unit. Um, Gravitational forces versus electromagnetic forces. Let's take a look at some of the similarities and differences. So your electromagnetic force uh, has attraction or repulsion between two charged objects. Your gravitational force is only attractive and anything that has mass will have gravity. So electromagnetic force is attraction or repulsion, and that's between two charges, and the gravitational force is only attractive, and that is just between any two objects that have mass. The electromagnetic force can act over a distance, so the two objects don't have to touch each other, so it is a distance force or a field force, and gravity acts the same way. So both forces are field forces, and they both act over a distance with a near infinite range. The electromagnetic force is much, much stronger than the gravitational force. And the gravitational force is the weakest of the four universal forces, so it is much weaker than the gravitational force. The fundamental rule of electrical phenomena, what I sometimes like to call the law of electric charge, is that like charges repel and opposite charges attract. So if you look at this diagram here, in the very first image of the two charged objects, these are called pith balls. They're tiny objects that we can give charges to. So the first one, the first set has two positive pith balls, and they are not touching each other. They're actually moved away from each other, so they're experiencing repulsive force. The second one has two negatives. Again, the charges are the same, so they're like charges. So again, they're away from each other, so they are repelling each other. However, if you look at the last one, one's positive, one's negative, so they are attracting each other. So they're going to experience that force of attraction that brings them together. So in general, charged objects. So when an object becomes charged when electrons are removed. You can also have electrons added, but we call this an ion, and it's just basically a charged atom. So if an atom loses an electron, that it has more positive charges than negative charges in it, and it becomes a positive ion. If an atom gains an electron, it's going to become a negative ion because now it has more negative charges than positive charges. There's a couple of materials you should be familiar with that become negatively charged. Rubber tends to have a negative charge, as does silk. These two will tend to have tendency to grab on to extra electrons from somewhere else. And now materials will become positively charged. These items don't like electrons and they just want to give them away. Glass, hair, fur, and then plastic. Those objects become positively charged. Just make sure that you're familiar with some of these. It'll make answering some questions a little bit easier as well as participating in the discussion. So just be aware that some items like to give away their electrons and some items like to get as many electrons as possible. There's also this idea called conservation of charge. Now, last semester, we looked at conservation of energy, conservation of momentum. In chemistry, you've had conservation of mass. It's the same deal. Basically, you cannot create or destroy any charges. Charges are not created or destroyed. Charges just transfer from one material or object to another. So charges are transfer, and they transfer by the electron. Only the electron can move. So just keep that in mind that your protons are tightly held in the nucleus and they are not going to move. And so what you're actually doing is you're going to separate charges to form these positive and negative ions or charged objects. So again, you're removing charges from one to the other. And keep in mind that it's very important that you realize that charges cannot be divided. They have to move in whole charges. So in other words, so let's say an electron has a charge. Let's say that there is a charge of 1.6 times 10 to the negative 19 coulombs. That is the charge of an electron. It can only move in whole number multiples of that particular charge. So you can't take that 1.6 times 10 to the negative 19 coulombs and divide it in half. You can combine it with another charge and have 2 times that number, and add a third one and have 3 times the number, but you can't divide it up into any smaller charges. So you always have to move in whole numbers. Coulomb's law is almost like gravity, but it states that the electrical force varies inversely with the square of the distance and is directly proportional to the product of the charges. So what exactly does this mean? It means the farther out you get, the weaker the force becomes between 2 charged objects. However, the more massive the more charge something has, the greater the force. So the unit of charge is called the coulomb. You heard me mention it earlier, and we use a capital C for the coulomb. And the electrical forces between very large objects tend to cancel out, but electrical forces between small objects can be very large. So, for instance, the electrical forces between, for instance, me and the ground were very large, so the electrical forces within us cancel each other out. But if you have 2 very, very tiny objects that are at the atomic level, that's when you're going to experience these very large electrical forces. Although I will say that the electrostatic force keeps you from falling through the floor. The equation for this looks very much like the one for gravity, except it's going to be the electrical force equals the Coulomb's constant, which you'll see is 9 times 10 to the 9th Newton meters squared per Coulomb squared. That's a constant. That number will always be the same, 9 times 10 to the 9. So it's a very large number. Times the charge 1 times charge 2. So you have 2 charged objects. You're taking the charge of the first one, multiplied by the charge of the second one in coulombs, and you're dividing it by the distance squared. So instead of dealing with masses like we did with gravity, this time we're dealing with charges. So Q is your charge in coulomb, D is your distance in meters, and K is your Coulomb's constant. Now in class we've already looked at a lab situation with conductors and insulators, and we're just going to take this a little bit further. But and if you haven't done it yet, there will be a lab in which you look at conductors and insulators. But conductors have the outer electrons, which move easily, and they're loosely held. So because these electrons aren't held very well to the material, they tend to move around very freely. Most metals are good conductors. There are some metals that don't conduct very well, but a lot of metals are good conductors. Insulators, on the other hand, hold on to their electrons very tightly, and they don't move around very easily. So you have glass, you have plastic, you have rubber, and you have wood. So these don't tend to allow electrons to move through them very easily. So so you may have noticed, so if you take like a battery, let's say, you hook up some leads to it, and you try to connect the light bulb up to it using glass, plastic, rubber, or wood, you should notice that any of these materials will not allow the light bulb to turn on. So that's a good test to determine if something's a conductor or an insulator by hooking it up to a battery, let's say, and see if the light bulb turns on. Semiconductors are materials that are insulators most of the time, but they have impurities in them which allow them to act like conductors. So for instance, silicon, which is most of our electronics have silicon chips in them, your computers do, your smartphones do, and under certain conditions, or when they have certain impurities in them, they become conductors. Germanium is another example, but the one that we use on a more regular basis is silicon, which is in most of our computers. Superconductors, though, are materials in which there is going to be no resistance whatsoever to electrical flow. No energy is lost to friction or heat. And most of these materials that are superconductors will have these properties once you take the temperature down to absolute zero, which is negative 273 degrees Celsius. So let's look at the methods of charging. One method of charging is friction. We talked a little bit about friction again last semester. But when you rub 2 surfaces together, sometimes depending on the surfaces that are rubbing together, electrons are going to transfer. They're going to jump from one object to the next. So it results in an object that has a positive charge and then another object that has a negative charge. And then the 2 objects then have this attraction to each other. That's why if you've ever taken a balloon and you rubbed it on the top of your head and then moved it away, the hair will stick to the balloon because you've given you've passed electrons from your hair to the balloon, and now the balloon has the extra electrons. Your hair doesn't have as many, and so they're sticking together. So that's an example. Also, other examples are clothes on a dryer, combing your hair. Most of the material that the combs are made out of will grab onto the electrons that are in your hair, and then your hair will stick to those electrons. Conduction. This is when you touch a neutral object with a charged object, and then that neutral object takes on the same charge, and then the two objects are going to repel each other. So friction results in objects attracting each other. Conduction actually results in objects repelling each other. And so until you ground that object, this charge is permanent. So if you look at the picture, the net charge on the object is 0. If you look at little part A. Now part B, I'm bringing an object that has a negative charge over to it. So what I've done is I've attracted the positive charge, I've repelled the negative charges. Oh, and I touch the object that's neutral, and I've taken on that charge, and now that object, the object, you see all the positive charges are lined up. I touch it with that negative rod, and now some of those charges have gone on over to the object, and now the object is negative. So we took an object that was 0, and then we caused it to take on a positive charge and a negative charge, and this was done by touching the object. So remember, conduction is by touching, by contact. So that C-O-N, conduction, contact. So remember that. You have to be in direct contact. Induction, on the other hand, is when you bring an object near something. You don't touch with induction. Induction, there's no touching going on. So you're going to bring the charge within a certain space next to it. What's going to happen then if I throw, like for this image, if I bring a negative rod over to the neutral object, it's going to cause the electrons to move to the other side, leaving me a positive side. Now, if I separate those two objects, one side is going to be positive now, one's going to be negative. So I didn't touch anything. I just separated objects once I brought something by to move the charges around. And all this is done by moving charges. And so now you have a object A will be positive, object B will be negative. So again, I did all that by the law of charges. Grounding. Now, grounding is the process of touching an object so that the excess charge can run off to the ground. Most homes have lightning rods. They used to have lightning rods in them. Now there's sort of these devices are built into the frame of the house. And what it does is if lightning hits the home, instead of it hitting the home and causing a fire or something, it will actually run through this conducting material and run down into the ground to create a safe environment for a home. Because generally lightning will strike the tallest the tallest object it can find. It wants the shortest way to go to the ground because the clouds get a charge on them, and they want to balance each other out. That's what things want to do that are charged. They want to balance out those charges, and the best way to do that is to run it into the earth, since the earth is you can consider the earth electron storage. So once the clouds build up too much charge, they want to connect to the earth so that way it can get rid of that excess charge. When you get shocked touching a door, is the same thing is happening. You move your feet across carpet, you touch a doorknob, oh, I get shocked. That shock is the charge moving from your hand to the door because you've built up some extra electrons on your feet by moving through the carpet. And that's just a miniature form of lightning. Lightning just happens between the clouds and the ground. A spark happens, or a shock happens between your hand and the doorknob. And again, I just mentioned lightning. So you have electrical discharge between the oppositely charged clouds and the ground. This is done by induction. So the negative charges will accumulate in the clouds, and the positive charge will accumulate on the surface of the Earth. And then there's a discharge, so the clouds will ground themselves to the Earth, just like you would with a shock, except the clouds are getting shocked by the Earth. Charge polarization. This only occurs in insulators, and if you bring a charged object near an insulator, it causes the charges to move within the atoms. So think of it this way: is that atoms become electrically polarized, which means one atom becomes positive, the other atom is negative. But it's still the same atom. It's just the charges have moved to one end of the atom. And so if you put a balloon, if you rub a balloon against your hair and then you stick it to a wall, the balloon will have the negative charges, and it's going to push those electrons to the other side of the wall. And so, and then the balloon will actually stick to the wall because the surface of the wall now has the positive charges, and then the balloon has the negative charges, and so then it'll stick. An example of a polarized molecule is water. And so here's a water molecule. And what will happen is, if you notice at the very top, the positive charges will stay up at the top, but all the electrons will tend to accumulate toward the other side of the molecule. So the oxygen atom will have a slight negative charge, but the two hydrogen atoms will stay slightly positive. So even though it's one molecule and it's electrically neutral, there is a charge imbalance. And if you haven't already seen it in class, will actually bring a charged object near water, and will actually be able to see the water water faucet. You're actually able to see the stream of water move in relation to that charged object, typically a balloon. So if you can charge up a balloon, take it near your water faucet, as water's coming down, you can see the water move ever so slightly due to that electric charge that's on the balloon.